So in this session today, let's learn about IPv4 protocol with the assistance of Wireshark. As we have learned, Wireshark is a powerful tool, which is a packet analyzer, which can be used to troubleshoot, but not only to troubleshoot, but also to learn about different protocols. This is the file I have downloaded from the Wireshark samples. You can go to download this file by going to the help menu and then sample captures. There you can download different protocol sample captures. So here, if I go to, of course, alternatively, you can go to capture and you can capture the live traffic by selecting any of the interface here. So this one, someone actually captured this and saved that such that we can understand different protocols. Now let me go to what are different protocols involved here. Let me go to statistics and protocol hierarchy. You see a lot of protocols are involved. What are those? This is, you can see this inside frame, which is used by Wireshark, but this is actual protocol, Ethernet. Everything is encapsulated into Ethernet layer 1, the data link layer, sorry. Okay, or in a TCP/IP model, which is a layer 1. In a voice model, it is data link layer. And here you have the IPv4 protocol, address resolution protocol, ARP. ARP is used to resolve what is the ARP protocol? ARP is the address resolution protocol, which is used by the systems, computers in the local network to translate the IP address into a MAC address or a physical address, because the routing happens in a layer 2 if you take a TCP/IP model, so we're in a network or IP layer, but in underlying layer, data link layer or network access layer, systems need what is called physical address or MAC address to communicate, to identify each other. But so in such a case, IP address would be so IP address is not helpful. IP address is helpful when routing takes place, but when packet reach the destination network, so we need the MAC address, physical address of the device that for the packet to be delivered. In such a case, ARP is used to resolve the IP address into the physical address. Anyway, we have different protocols. You see, IPv4 protocol. So inside IPv4 protocol, top layer protocols are encapsulated. That is what we have learned, right? So what are these? This is a user datagram protocol, UDP and TCP. Inside UDP, you can see DNS protocol also. All of these are, whatever you see here, all of them are application layer protocols. Can you see them? DNS protocol, DHCP protocol is the dynamic host configuration protocol, which is abbreviated as a DHCP. So net bias protocol, real-time RTP, RTCP, RTP, SIP, session initiation protocol. These are all application layer protocols. We talk about the TCP/IP model, or if you talk about OSI model, these are all application layer protocols. Application layer protocols are encapsulated into which layer? Transport layer, right? So you see, transport layer, how many protocols we have? We have two main protocols, UDP and transmission control protocol, TCP and UDP. And TCP UDP is encapsulated into what? IP layer. IP is encapsulated into Ethernet, data link layer, right? So same thing, let me show you that same thing. This is, I've learned about this protocol encapsulation and decapsulation, right? You see the data which is encapsulated into another layer, right? This is what we have learned. You can see, and that is encapsulated into, let's say, network transport layer, and transport layer data is encapsulated into payload of network layer, and network layer, the whole packet is again encapsulated into a data link layer, and physical layer, network interface controller, converts that into but yeah, bits, and they are transferred. So this is what we have learned. We have the data in a top layers, and the data and the in a transport layer, that the data is put into placed into the payload, and the TCP header is added, and both the transport and everything is actually placed layer used as a payload in underlying layer, network layer, and the IP header is added, prefixed to uh, the TCP and the data we have. So right, and then that is encapsulated into data link layer, and bytes are transferred, and when it is decapsulation happens, uh, data link layer removes the Ethernet frame header, and yeah, and gives to the network, and it removes the IP header, and that service gives it to the transport layer, and then finally application receives that. Same thing we can see if we go to protocol hierarchy. That is what we see there. Protocol hierarchy, that is what we see, different protocols. And now let's learn about IPv4. What is IPv4? IPv4 protocol. So we can learn about different protocols, DHCP, DNS. These are different endless application layer protocols, hundreds of application layer protocols. But TCP IP suite to set up protocols for these things to work on internet. So those are limited set of protocols that in a transport layer you have either TCP or UDP. In a network layer that can be either IPv4 or IPv6, right? So here let's learn about IPv4, and then learn about UDP. Okay, so uh, so if you take the IPv4 protocol, so I would like to. So IPv4 is a network layer. So if you take any protocol here, which means that there is a definitely the IPv4 out there, right? Unless uh, unless it is a protocol in a data link layer. So IPv4 is involved, okay, in every protocol. So now let me take one simple DNS. Let me take a DNS query. I just need a okay, and so here is the data. Okay, I have filtered DNS because it involves less data, so we can actually easily learn about that protocol, IPv4. So this is a complete frame, right? Do you understand? Complete packet, whatever you see here. Now, so first let me show you what is IPv4 header is like. Okay, so IPv4 header is like this one. IPv4 header, so IPv4 packet, so PDU, what we call the PDU, protocol data unit in application layer, which is simply the data. But when it comes to the underlying network layer, in a transport layer, they are called segments, right? So, but in a network layer, what they are called? They are called packets or datagrams. Okay. So in an underlying physical network access layer, they are called frames. Okay. So we have learned the PDUs. Let me refresh your. See what it is called in upper layers. It is called simply the data. In transport layer, it is called segments, and in network layer, they are called datagrams or packets. In underlying layer, they are called frames. And we have this IPv4. This is called a packet or a datagram. This packet, how this packet is structured? This packet is, see, this is a protocol. So what are we talking about here? Each protocol contains three things, is formulated by three things. That is syntax, semantics, and timing. Syntax is how it is structured, semantics how it is interpreted, and timing when to send, when to receive. And here we are looking at the syntax or the structure format. So it has the IPv4 packet, has a header and the body. So you may call it as a header and a payload, or header and data. So the header is prefixed. Header is preceded by the data of that packet. So here there is a fixed length header, and there are actually 0 to 40 bytes of optional uh, padding or options. Okay. So how it is structured? We have a, so what is a minimum length of IPv4 packet? If you don't think if you think there is no data, if you consider, let's assume there is no data and there are no options, what is the minimum length of IPv4 packet? 20 bytes. And let's say 20 bytes and you have 20 bytes options. So how much is the header length, header size, which is a 40 bytes. And then you can have a data up to 65,536 bytes. Okay. Okay. So here, let's discuss about a header here. What we have, see, this is structured this way. We have a 0 leftmost bit and rightmost bit 31. So there are actually total 32 bits. Do you get it? Okay. The first four bits are used to represent the version. Second 4 bits are used to represent IHL and the quality of service or service. Next, 8 bits are used to represent the service. We'll discuss in depth about I'll explain about what in detail. And what we have is a next total length. What is total length? Total length is a length of the total length is the length of the header plus data. Okay. So how many bits or how many bytes of so for suppose if you are actually sending this without having a length, the receiving end doesn't know how much it is receiving. So we need a length. Got it? So, and the next one is identification. Those are called, see, first one is remember this way, first row, we have actually information about the service version and length. And second row is about the fragmentation. Okay. Second row is about a fragmentation. The fragmentation doesn't happen much here. Okay. So fragmentation means when size exceeds, fragmentation nowadays much doesn't happen. But fragmentation sometimes it is required. IPv6, when it comes to IPv6, it doesn't recommend the fragmentation. It is structured that way. But what is fragmentation? For suppose how much data you can put into the one packet here, you can put only 65 kilobytes. 65 kilobytes. But when data is exceeding that, what you need to do, you need to fragment. You need to actually break that into multiple packets again. Okay, so in such a case, it means it protocols, it doesn't exceed. It doesn't mean it does. Nowadays, fragmentation doesn't happen. Fragmentation happens when it happens, when actually packet byte is packet size is big. Okay. Packet size is big, but there's softwares and hardware they happen to handle intelligently. But so if fragmentation happens, what is the situation here? Whole packet is again broken into multiple chunks called fragments. So when receiving end is receiving those chunks, it should be able to actually put those all chunks together. So in such a case, it needs the information for those about those fragments. So each fragment is identified with the same number. Okay, identified with the same number, and these are flags about the fragmentation, whether to fragment or don't fragment. Fragment offset is actually it describes which let's say if you have fragmented, let's say system fragmented. See, this fragmentation happens based on another unit called there's actually limit. Just sorry, size. In different networks, that size is actually varies. So some networks are able to carry the bigger packet size. Okay, some networks are not able to. In such a case, hello, can you hear me? So in such a case, actually fragmentation happens. Like let's say that packet is traveling from one network to another network. But there is some network out there, it is not able to carry the very big jumbo packets. Okay, so in such a case, what happens? Those packets are fragmented. A big packet is actually divided into multiple packets, multiple fragments, and a receiving router will construct a packet back from those fragments. So if you have four fragments, what happens? Let's say what happens if you have four fragments? Fragment 1, fragment 2, fragment 3, fragment 4. Likewise, we should be able to identify that. So this fragment offset is used set in that packet to identify where that packet is actually comes when that packet is being reconstructed. Okay, that it is offset of that packet itself. Okay. Which one? Yeah, flags there are 3 flags. Okay, so there are actually, let me, so the packet format or packet structure, there are 3 flags. This is actually generally provided there, but if you go on some side, there are actually, these are flags, 3 flags. Those are just 3 bits identifying whether to fragment or not. Okay, so and what you have next is a time to live, which is what is that? Which is because this packet travels from source to destination through different networks, which means different routes. When each router it crosses means one hop. Okay, each router it crosses is a one hop. So sometimes if it is not routable, it might go round and round forever, traveling and not reaching the destination. That might happen. Do you understand? So there are actually due to loops, it might lost and going like forever, and it might last. So that this time to live indicates how much distance it should travel. Okay, when it reaches 0, it will be decremented for every hop. When it reaches 0, that will be dropped packet. Okay, so no, it won't show for every hop. For every router that is passing this packet, that actually decrements this. So likewise, it will be decremented. So here you can see time to live 8 bits. Okay, so 8 bits are used for time to live when it reaches 0. Okay, so that will be that packet won't be delivered, forwarded further. Do you understand? That will be by sending a error message through ICMP. There is a ICMP protocol. Packet can't be reached. Packet not reachable. Some error message will be sent back. Okay. Okay. So, and here we have a protocol. Which protocol? It is actually encapsulating a TCP or UDP. That is actually is provided here in a protocol section. Okay. There are, for each protocol, there are bits here. Do you get it? Okay, for each protocol there are bits, so it indicates what kind of protocol it is encapsulating, TCP or UDP. And next one is a header checksum. What is header checksum? Header checksum, why do we use checksum? So see, packet is traveling over different networks and it might actually corrupt over the time, as it is going over different networks. This header might corrupt, might get corrupted. In such a case, we need to be able to verify when it reaches the destination. So corrupted means not hacked. Corrupted means, let's say that for example, if you are actually writing over the DVD drive, you're writing the DVD drive, sometimes, because of that, some hardware issues. I'm giving you some example of corrupt, different use cases are there for corruption. For suppose because of hardware issues or software not able to write properly, those bits, the data you write into the Blu-ray disc or DVD drive might get corrupted. Do you understand? Might not be able to reach onto that surface properly. Likewise, if it is traveling over different networks because of some interference on a different mediums, or do you understand? Because of some interference, because of some networks, whatever that reason can be. For suppose if this header is actually, for suppose this header is, how many bytes it has a total? How many bytes? 20 bytes. So 20 bytes means how many bits? 160 bits. Right. So 20 bytes, each byte has means 8 bits. Total 160 bits we have. For suppose out of 160 bits, if one bit is flipped from 1 to 0, it means that it is corrupted. Do you get it? So for suppose it has a protocol information. It has a UDP protocol, but that bit, there are 8 bits that describing the protocol, but that bit is flipped from, let's say, 1 to 0. That might actually be referring TCP instead of UDP. In such a case, receiving end may not be able to properly process this packet. Got it? So, for that reason, what do we need? We need a mechanism that receiving end should be able to. Of course, you might ask one thing: what if this header 16 bits itself? This is a 16 bits. 16 bits are used to calculate the checksum. It calculates the checksum for the header only, not for the data. Okay, so if you may ask the question, what if this header itself is corrupted? Of course, you can't do anything. Okay, so that receiving end might reach some corrupted packet. It might drop or it might process that corrupted packet that way itself. Okay, so that is the reason sometimes you get unexplained error when transferring data. When you download, do you get it? So that header checksum 16 bits are used to calculate the checksum of a checksum which is used to verify the integrity of the header. And what you have next, you have a source address, destination address. Source address means source that is sending the packet, IP address of the source computer, and IP address of the computer that packet is destined to. Okay, so the packet is destined to. And here what we have is a HL, okay, version that service describes. Uh, this is a IPv4 and IPv6, both protocols are best effort protocols. So it tries its best and it is actually connectionless protocol. Okay, and it tries its best for that packet to be delivered. And what we have IHL, this is referred differently, which is it is a length of the header. Okay, it is also sometimes it is referred as header length. Okay, so it is actually multiples of counted in multiple of words. Okay, header length. I will explain you that in detail. Okay, we'll see. Okay, so this header length, how many words you need to compare, you need to multiply with the 4. So how many words, what is a word here? So how many bytes we have here? 32. So 32 means 4 bytes. 32 bits means 4 bytes. Okay, what do we call 2 bits are called? No, 32 bits. 32 bits we have, which means 4 bytes. 8 bits are called 1 byte. And 2 bytes can be called are referred as a word, or sometimes 4 bytes are also referred as word. Okay, so these 4 bytes are referred as a word. Word. Okay, so total how many watts, minimum how many watts that this IPv4 packet header contains? 1, 2, 3, 4, 5, right? 5 watts. Do you get it? 5 watts. 5 into what means 4 bytes into 8, you get the 160 bit or 20 bytes. Okay, so have we covered everything here? Version, which is describes IPv4, IPv6 header length, and it is a service which describes there are different flags, different service describes which is the best effort, priority, like that will be provided or mentioned in the service. Okay, so like a quality of service flags or a set in a type of service field, and you have the total length and identification. These 3 fields are used for fragments. Okay, can you hear me? Okay, yeah. So this fragmentation happens you due to the MTU. Okay, so MTU, which is a that varies between networks and networks. Let me actually show you that thing as well. So MTU, there we go. So can you see here? These different networks, some networks can't be able to handle the packet size. Some networks handle. You see here the length of 1500 only. Okay, but suppose some network is actually, you can see the MTU of your system. Okay, let me show you. Let me MTU of your system. So it is usually be the 1500. Some systems, it can be big, and so what happens if it is small in some systems? What do you get it? some networks. So IP, what happens? IP will packet would be fragmented. Can you see here as it is shown in this picture? Total length is actually 5140, but this packet IP original IP datagram is fragmented on a network because it doesn't handle that network doesn't handle this much big packet, so that is fragmented as a 4 packets, and the maximum length that this network can handle is a 1500, which is called a maximum transmission unit. MTU stands for. Okay, so okay, it is called maximum we don't want this IPv4. Okay, do you understand? Okay, that is where this fragmentation happens. Okay, so we discussed the what we discussed. We discussed the header, and there we have options. Okay, we have options. Options were actually optional data. Anything that this header you want to mention something else like a quality of service, and you want to some mention anything that is not you want to provide some meta information, but header fields are not enough. Those are fixed. In such a case, we use options to specify any other data. Okay, now let's I think and options may also actually be used to provide some routing information as well. Okay, options can also be used to provide some routing information and other things, but we'll see when we dig deep into that. And now let's go and check here. Let's take this packet. Okay, let's take any packet, and can you see the source and destination? What is source? Source is, what is source? 192.168.1. And what is this? What is destination? Yes, destination is 190.168.1. And so we see that packet, and yeah, both are in the same network. Okay, so both are in the same network, and so you might say it is 1.2, it is went to the 1.1. So go to the statistics, and you can go to here endpoints. There you can see what are different endpoints involved. Ethernet, IPv4. Can you see different endpoints involved? Endpoint means anything that can be source or destination. Okay, and go to statistics, and you can check, go to conversations, and there you can see the conversation between different endpoints here. Okay, see source address A and source address B. There are how many conversation, how many packets. This is a summary from 1.2 to this 255. There are 1.2 packets. Likewise, and 1.2 to 1.3, these many packets and this many bytes are transferred, according to this. Okay, so you can actually, let's say you want only details that 1.2 sent to 1.1. What you can do, you can hear me okay, right? What you can do, you can right click and apply as prepare filter selected. You want to see only conversation for that 1.2 and 1.1, because that is there you see the overwhelming of data. If you click on this one, you see that filter is applied there. Filter. Okay, And if you click on enter, and you see that data only. Can you see? Okay. So so this standard query, it is a DNS protocol. What we are looking at is a DNS protocol. Anyway, so let's select this one, packet, and you have 1.2, and probably this might be the gateway, right? 1.1. No, 1.1, 1. By convention. Okay. Hello. Yeah. So that is we selected this one. Okay. And let's go here. This is a DNS. We're not interested in DNS. Okay. This is a packet. As I selected this one, this is a whole packet data. That is what you see this here, right? Whole frame data here. Got it? Hello, do you get it? Okay. And here is the DNS query. In the whole packet, DNS query. Can you see this DNS protocol here? That is highlighted here. Okay. Let me select another layout here. Go to preferences, go to layouts, and it might be helpful. I selected this one. Okay, now check. This is DNS query, whatever is highlighted here. Got it? Which is application layer protocol, and that is encapsulated, and you have here UDP. Can you see UDP? Okay, and UDP protocol has a header and the body. What is the body here? You can see this. This is a UDP protocol, and the length is a 52. 52. Okay. And you see UDP this is the total length, and payload is 44 bytes. Your UDP payload. Okay. Remember this application layer protocol, that PDU called as data. That whole data is encapsulated into UDP as a payload. Can you see this? Okay, that is a payload. This payload itself is the DNS protocol. Can you see that? Okay, this is a payload is 44 bytes, and if you select the DNS protocol, that is also 44 byte. In status bar, you can check that. Okay, you can check that, and in a status bar, you can check that, and here, since we are discussing about IPv4 protocol, go to IPv4, and this you can see IPv4 protocol header. That is highlighted here. Can you see IPv4 protocol highlighted? And if I extend, you see the first bytes, what it is telling? Version. Can you see here? Four out there, here. This exact byte is this place. Describe the IPv4 version, which is 45. Okay, what is 45? Which is hexadecimal 45. Okay. It is dumped as hexadecimal. You can see, you can dump as a bits. Okay, and what is the header length here? What is header length? 20 bytes. Okay. Okay, so this whole thing is 8 bytes. Remember this, remember. And you see, out of 8 bytes, 0100, What does it mean? Can you see this whole packet here in IPv4 packet? How many bits are representing version? 4. How many bits are used to represent? 4. Header length? 4. Right? And how many bits are used to represent the service? Type of service? 8 bits. And so out of first 8 bits, 4 bits are called nibble. Okay? 4 bits are called nibble. So first nibble is used to represent version, and second nibble is used to represent the header length. Okay? So here you see this. First four bits, and convert that 8421, right? 8421. So convert that, which is a 4 IPv4. See here, first 8 bits are highlighted. Can you see this? Can you see? Right side. Yeah. So dump this as a hexadecimal, and 4 means 45. First 8 bits. 4 means IPv4. 5 means how many watts? This header length, which counts the length of the header in number of watts. It counts in terms of watts. So it is a 5, which means 5 into 5 watts. 5 into 8, which is 20 bytes. If it is a 6, how many, what would be the length? Yeah. Okay, so got it? So number of watts. So watt means 4, right? 5 4s are 20. Okay. So let's say that what would be the length of, what would the value? What is the maximum length of the header? You have a 40 bytes padding, and minimum 20 bytes for a header length. And if you, in such a case, if you combine total, length would be 60 bytes, right? So in such a case, the total header length, we would see there 12. 12 means in hexadecimal format. Okay. Hello. C, right? We would see there C. And are you getting it, or are you lost? Hello. Okay. In hexadecimal, yeah. So here, let's say that we have a 7. If that represents 8, let's say 8. Okay, the total length would be, header length would be 40 bytes, because 8 into 5, 40. Here 5 into, sorry, 8 into 4, which is a 32. Okay, here 5 into 5, which is 5 watts. 5 into 4, 20. Okay, so 40 bytes in such a case. In such a case, we would see that 10 into 4, 40. Here it would be 10. Okay, now let's move forward. It don't be confused. Just 4 bits are used to represent the header length, and so whatever number you have, just multiply that with 4, and you get the total header length, because this is used to count the header length in terms of watts. So watt means here we are using 4 byte watt. And since it is a 5 here, 5 into 4, and we get the 20. And if it is 10 byte, 10 into 4, which would be 40. Okay. Okay, now go to next length, differentiated service. It is also called type of service. Okay, here flags are used. How many total 8 bits are used to represent this service? Can you see here 0 0? Okay, here those are highlighted, right? And click on header, you see that whole bits that are actually representing the IPv4 header here. Okay, so right side. And total length. What is total length? Total length of a header plus data. Yeah, total length of headers and data, which is represented using 16 bits. Represented using 16 bits, and so here what it says 72. Okay, so out of 72, let's do some calculation here. These are called here it is a packet bytes. Okay, panel, which is a packets bytes. It is a packet bytes panel. If you select any of the packet and you see the actual content that is being transmitted over the network as a hexadecimal. These are that is a data. That is a data which is dumped as ASCII here. Okay, here you can see this. Okay, so sorry. Yeah, ASCII. So you are take this 45. You are seeing equivalent ASCII there. Okay, so remember, go to this our site. What is 45? Here you can see E, which is E. Okay, yeah, uppercase E, which is corresponding byte is shown as a ASCII here. Okay, so it is called hexadecimal dump, and you can see this by going to show as a hexadecimal or show as a bytes. And you can see here, if you show as a bytes, and you can see show text based on a packet or ASCII. You see ASCII. Can you see here? Or EB set. If I select, that is another character set, EB CDIC. This whole thing is changed. Can you see? Now you no longer see there for 45E. Okay, so we are just dumping that. So these bits are actually interpreted as a ASCII, and that is where you can see this in a DNS. The query it is asking zip dot. It is what it is a query. It is asking, right? Can you see it is asking about name zip UDP zip cyber city.dk, and that is what you see here in a query. Got it? Let's do some calculation here, which is a total length. And go to, okay. Here, you can see my screen. Can you see my screen? So here, what is the total length? 72. So total length, which is including both header and body, or a header and payload, right? So out of 72, remove 20. You are removing header. And what is out there? How much is out there? 52. Okay, right? 52. And you, which is a 2 bytes here, total length. Here you can see 20 bytes here, right? Here in a status bar. If we go to user datagram, how many bytes it is? 8. That user datagram protocol is encapsulated into IP, right? In such a case, remove that 2 bytes as well. 72 minus header of the IPv4 and header of the UDP. How many bytes? 8 bytes. Header of the UDP is fixed 8 bytes. And how much we got here? And can you see that exactly 44 bytes are of data? Yeah. Here, what is the total length of the IPv4 packet? 72. And which includes total, which means it represents the both length of the both header and body, or header and payload, header and data. Okay, whatever. But we are trying to calculate what is the length of the body. How much length of the body it is calculating in bytes. So it is 72, and you can see that that is represented here. Go to internet protocol. If you go to total length, and total length is represented using 16 bits, which means 2 bytes. Can you see here 2 bytes are highlighted? 2 bytes are highlighted. Okay, and 2 bytes are highlighted. So we're trying to calculate how much body this this packet is carrying, how much data, length of the data this packet is carrying. So we want to remove the 20 bytes that we can actually get it from the header length. Right, this is the header length, 20 bytes. Huh? Just recall this IPv4 packet, 20 bytes or header. We have no options, so 20 bytes only. So we are calculating how much data this IPv4 packet is carrying. Okay, including UDP header and excluding UDP header. Okay. See, minimum 20 bytes. But if there are optional options, there are actually options out there here. If these are actually provided, if these options are used, these options can be 42 0 to 40 bytes. If they are added, that is what we discussed last time, IHL, header length. Okay. Yeah, maximum these options is 40, which means the packet length can vary from 0 to 60 bytes. Okay, minimum 20, and if you think all options are used, 40 bytes. So 40 plus 20 would be 60. Got it? Okay, and the options are 0. Okay, so that you can actually identify based on the header length. If a header length is more than 20, which means that we can subtract from 60, if you can subtract 20 to get the options length. Yes. Okay, so that is the reason from total length I am removing 20. So what I will get, I will get the payload length, which is a data length, which is 52. Okay, and that is what it is. If I go here, there is a source, destination, this whole thing is data. And if I select the UDP datagram, okay, and you can see the checksum length 52. That is what we got, right? Yeah. So, but you want the length of actual data, application layer and protocol. In such a case, you need to remove the length of the UDP header as well, UDP protocol header as well. Okay, UDP protocol always uses the pixel length, okay, which is very simple. Okay, UDP protocol always uses the pixel length header. You can see this UDP datagram structure. You have a just a 1 2 3 4 fixed. There are total 32 bits, and first which means first 16 bits are used for source port and second 6 are used for destination port, and again next 16 bits are 16, right? First 16 are source, followed by another 16 destination, and which means that four bytes, and the next 2 bytes are used for length and next 2 bytes are used for checksum. So it is fixed always, UDP datagram. Okay, and followed by the data. Okay, this is a header structure of UDP. So always 8 bits. So we are using 8 bits. So we are removing that 72 minus 20 minus 80, and you will get the 44, which is the length of the actual data, excluding the header of the IP, header of the UDP. We get the length of the actual data. Okay, actual data or a application layer protocol, and you can see the same thing here, 44 bytes. Okay, so yeah, now further dig into the IPv4 protocol. You can see the length and you can see the identification. Here identification, this number which is 16 bits, that is used to identify the packets itself, to identify this for all, you know, this identification would be same for all fragmented packets, and for each packet it would change. So when receiving end is reconstructing, it will reconstruct a packet from fragments by identifying packets with the same identification. Okay, so if it received 4 packets with the same identification number, which means all of the 4 packets are actually fragmented fragments of a big packet. So in such a case, all of them are actually reconstructed based on the offset here. Offset of those packets. Okay, this is identification, and for different packets, if they are not fragments, for every packet, this would change. You can actually verify that. Can you see that identification is changing here? Okay, so you can see, we will see the other day how fragmentation. Next day we will see the fragmentation as well. Okay, now yeah, that flag is 0 0. What are flags? This hello, yeah, there are flags. 3 bits. 3 bits are used for black flags, right? We have seen 3 bits. Those 3 bits are used, set here are there, that we have, DF and MF, do not fragment and fragment. Those are the flags that are used. So if do not fragment, if it is 0 0 means do not fragment, which is not a fragment, which means, okay. So here it is not a fragment, and you see that is the reason offset is 0 0. Everything is 0. So far, any questions? Yeah, those are three those are 3 bits, and we will further discuss in detail about the fragmentation. There are 3 bits, and one is reserved, and so other 2 bits do not fragment and fragment. Okay, here you can see. So, and do not fragment means so don't fragment this packet. Fragment means, so if that bit is 1, it means that that is a fragmented packet. And for a last packet, it would be 0 0. But for a packet that is not fragmented, it would be 0 0 also. If it is not fragmented, offset will be 0 0, because this is not a fragmented packet. You see this here, all are 0, offset is 0. Okay, and here time to live, which is 128. Okay, so for the next hop, it would decrease. Okay, so let's actually check the time to live here. Time to live, there is at 64 here. See, time to live 50, 55 here for something here. Hello. Okay, it varies. It varies for every hop it travels, that is decremented. It is coming from the internet. Can you see here, public IP? Okay, so over the internet, for every router, it is for every router, that is uh where where here 32. Oh yeah, this is ARP protocol. Okay, these are actually, you are seeing this destination, their domain names, they are resolved here. Okay, host names. Okay, so can you see they are resolved? Okay, if you go click and you can see the resolution there, you can see the MAC address as well as no IP address, and it is a broadcast. If it is a broadcast, or if MAC would be 0, we learn. Okay, RP is used to resolve the IP address into IP address into uh, MAC address. So he is asking, the source. It is asking who has the 192.168.1, 1.2, and so if anybody is having that IP, so report it to 1.1. Okay, and here is the response here. He is actually, here is the response. So 1.2 is with the MAC address, so on, so MAC address. So this thing happens in our network all the time, because how come this MAC address is required for packet to be uh, delivered in a network, right? Okay, so how come, let's say your phone and your router, Wi-Fi router, and how come your phone knows the MAC address of Wi-Fi router? Because the phone asks the MAC address through ARP, address resolution protocol. Okay. So we were discussing what? Yeah, packet 10 and the time to live. Okay, this is decremented every time the packet is uh, forwarded, and in IP v6, it is, instead of calling time to live, it is called as hops. Okay. Okay, and can you see the protocol here? Protocol. Okay, so which is 8 bits again to represent the protocol. So 17 means 17 means UDP. Okay. There are protocol codes. Okay, let me show you that. Can you see here protocol codes, protocol number? Okay. So if it is a TCP, we would see here what? 6. Okay. Okay. So, okay, that is how I actually nodes receiving and actually identify the protocol. And you have here the header checksum. Can you see header checksum? The 16 bits, which is the 16 bits calculated for a whole header. And this is validation. We haven't validated this here. We can do the validations. We can enable validation or disable in preferences, but does not recommended that consumes a lot of processing power. And here checksum and the source address. Can you see source address? Source address represented in a here source IP address represented in a hexadecimal format C080102. Okay, and destination address, which is again 32 bit, right? 32 bit. You see the 32 bits here highlighted. Okay. And this is IPv4 header. And the payload has our data has a UDP and data, which is a DNS protocol. Both are encapsulated into the IPv4 data. Okay. So what this data contains, what here, what this data contains, both the UDP as well as what this data contains UDP, and UDP has the data. Got it? This data contains, or it is a payload of IPv4. It has it encapsulates the UDP, and UDP encapsulates the data application layer protocol in its payload. Got it? And you see, this is how you can see this the whole thing that you are learning, whatever header, body, different protocols, OSL layer, all those things you can see with the help of Wireshark. You can see them in action, and you can have hands-on. And this is used to troubleshoot, but not only troubleshoot, but also to learn and dig deep, understand protocols in detail. And more than anything, you can see that protocol data in bits, so that you can see actual bits, and you can actually really understand. You might be actually see, it might be helpful if you are learning this. I might be actually telling this is a header 32 bits and so on, so. But if you see that in action, you know, that might actually register click. Well, understand, you can understand that very well. And let's say I displayed this as a bits, and if I go to internet protocol, let's check this 192.168. Can you see this here? IPv4 32-bit address highlighted, right? And if you go to tool, there's this one. Where is convert binary to dotted decimal? Here. Give 190.168.2.1. And can you see the same one? And that is what you see there, right? For 190.168. Got it? Got it? And this is a data that is, those are the bits, those are actually transferred. This whole data is a packet, one packet. Okay, that is transferred, traveled across the network, and this is a DNS query, travel from this to the DNS server. Yeah, he was asking something. Okay, do you have any questions so far? And you can download these tools, those capture examples. Go to sample captures, and there you can download those sample captures and explore. And if you don't have those, see, this is helpful if you are in a situation where you can't use the Wireshark because of permissions. Where for a Wireshark you need admin privileges. Let's say you are using Wireshark, but in a laptop you don't have admin privileges. In such a case, you can't capture on every network. In such a case, you want to learn. In such a case, you can download that. Sample captures available here and explore and learn through this. And this is the best way to learn about protocols with a hands-on experience using a Wireshark.